address these stochastic deviations. We discuss the application to real-world data, compare it to prior methods, and present a complementary visualization.
As data is changing, our understanding of data should be updated correspondingly. Based on machine learning approaches, we formulate a drift-level index to monitor the evolution of multi-source data, which allows users to capture and reason significant changes from time series data. The proposed visual analytics system is called Concept Explorer. More details can be found in our talk.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
After determining the departure timestamp, the experts then moved to verify the recommended shuttle stops and routes. Note that Shuttle VIS recommends the default shuttle stops and routes based on the metric of average distance. Then they observed that in our cluster 4, the system recommends Hejian as the shuttle bus stop, but the experts identified that another drop-off spot Panshanhuiyuan is located in the middle part in this regional cluster.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Our research goal was to design an efficient preview method of the parallel vectors operator through direct volume raycasting. As such, we present the first implicit raycaster of parallel vectors feature curves that reaches real-time performance for interactive parameter exploration and preview by applying tensor product calling and a sectional Newton descent.
VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
Programmers often make mistakes like this. A VIS function is incorrectly called with a string. A programming language can catch such mistakes early on, but for this, it needs a type system. We present Typical, an interactive visualization tool for programming language designers. Typical allows them to explore common function type signatures and helps create a type system.
The recent COVID epidemic has triggered several different crises that are testing our civilization's potential for both coordination and cooperation. Data about infection rates and their growth has been the main source for public discussion and has inspired many visualization works. We propose a VA approach that incorporates a growth predictive model. This allows the correlation monitoring of the virus population development. We also can relate it to different government response events, as well as identify key dates.
Interacting with large datasets could be painfully slow. We can reduce the latency with faster backends, but that's not always attainable. Here, we investigate a solution that only leverages techniques on the front end. We propose interaction snapshots, where users can view the results at a later time. We found that users experienced much less frustration and were able to complete the tasks faster.
Billions of biologging records reflect animal behaviors on many temporal spatial scales, yet segmenting the time series on multiple scales is often avoided or impeded. Hence we present our multi-seg VA platform with its 3 contributions. First, multi-seg VA contributes tailored visual interactive features for multi-scale segmentation. Second, we show a new visual query language to flexibly configure scale-wise techniques and parameters. This VQL consumes a domain-oriented set of techniques, our third contribution.
In human brain mapping, atlases are indispensable tools to neuroimaging experts. While many of these atlases capture general trends over large populations, they fail to capture subject-specific complexity of brain organization. We propose Pragma, a tool for interactively deriving individual-specific brain maps from established atlases. Pragma supports within and between parcel analyses to help experts make decisions during the parcellation process.
How do we represent remote users in synchronized visualizations while supporting divergent exploration? We present cursors, the basic unit of user representation in a collaborative visualization. They can vary significantly in appearance, as you can see. Cursors enable collaborative interaction techniques, such as peeking, tracking, and forking. To learn more, please read our paper representing real-time multi-user collaboration in visualization.
We present our work, Visual Analytics-based decision-making environment for COVID-19 modeling and visualization. In pandemic situations like COVID-19, public health officials have to prepare and evaluate response plans. They need tools to explore and compare model simulation outputs, study different spread scenarios, and analyze the impact of mitigated decision measures. If you want to know more details about how we support this, please attend our talk.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
Hello, everyone. Welcome back to VIS4DH. This is session 4. It's our final session of the day. In the session, we'll have 4 paper presentations, followed by 6 lab talks, and then, of course, our closing at the very end. So I'll start with the papers. The first one is entitled Bio-Inspired Structure Identification in Language Embeddings. It'll be presented by Zhou. And his co-authors are Oskar, Elek, Pranav, Anand, and Angus Forbes.
Hello everyone, our paper name is Bio-Inspired Structure Identification in Language Embeddings. My name is Hongwei Zhou, and welcome to our talk. Here is an overview of our talk. First, we're introducing an agent-based model to word embedding data, and we'll talk about that in the following slides. Second, we talk about this method as a new way to identify a relationship between word tokens. We also compare our method to traditional methods in natural language processing. And lastly, we demonstrate how our method reveals new geometric configuration in the data and open a new line of inquiry into understanding the structure of the data. So here's our motivation. So first, very briefly, we're embedding data are word tokens, such as black as a noun, and transform to points in space. One typical assumption when we're embedding data is that closer the word vectors are to each other, the more similar the transformation algorithm identifies them to be. And second, we're inspired by the principle of least effort, which can be identified in many phenomena such as light transport to the behavior of living things. We'll talk about how our method uses this principle to generate optimal transport network in the following slides. And lastly, we are assuming that the relational structure of language is reasonably preserved in the embedding representations. In other words, we are assuming the result we extracted from this method does correspond to real patterns in natural language in some way. Our method is called Monte Carlo Fisher machine, or MCPM. It is originally a very rough modeling of slime mold introduced by Zhou. You can see one such slime mold in action on the right. It was then modified by Oskar Elek with a Monte Carlo mechanism, which were proven to be super useful in conducting structural analysis of cosmological data. And Mr. Elek will also present his research in VIS 2020 later this week. Also, to briefly introduce MCPM, the method takes in data points in space as input. These are equivalent to food for the slime mold, where the slime has to figure out a way to reach the food with the least effort possible. And for output of MCPM, we extract the trace, or the path. This trace is generated by an agent while they explore the space, and also 4 agents to travel through. Conceptually, we can think about the trace as highways, and also, as mentioned, optimal transport network. Mathematically, we can simply think about the path as average agent density, or the throughput of the network guiding the agents. Just like how roads, where bigger throughput means higher number of cars traveling through it. Our agent is a very simple traveling agent with Monte Carlo steps. At each simulation step, our agent samples 2 cells from the deposit field, one straight ahead of its travel direction, in this case P0, and one a little bit off its travel direction P1. The P0 and P1 will determine the probability of whether the agent is turning. So the bigger the P1 is from P0, the more likely the agent will turn. So generally, this simple agent behavior makes the agent travel mostly guided by the deposit field or the trace, while still giving a slight chance of deviating from the trace. And so in Monte Carlo method, this is the distinction between exploitation and exploration. For the deposit field, or the trace, we start out with the only deposit at the data points. When we release the agents, they will also store a small amount of deposit into the trace field. Over time, the path will be formed in the deposit field by the agents. Eventually, the trace will stabilize. A highway network very similar to an optimal transport network is formed in the deposit field. We then export this field and allow our agent to simply explore it without ever changing it. So this is a comparison between trace-guided travel and trace-unguided travel. Let me just introduce the graph real quick. So the blue is where all the agents are spawned, and the gray are the trajectory of the agents, and the green are word tokens or data points or food undiscovered by the agent, and the red are the food that are discovered by the agents. As you can see in the trace-guided graph, the agents form coherent paths and explore further into the clusters on the top left. We mark the 2 areas A and B to demonstrate that difference. Both areas have the same distance away from the spawn point, but A is more thoroughly explored since it has stronger connection to the spawn point. So we apply our method to 2 different word embedding datasets. One is from the language model BERT, and the other is from Genshin Continuous Skipgram, a variation word to vec. We refer to BERT as contextual embeddings and Skipgram as global embeddings in this talk. For contextual embeddings, one of our results is shown on the right. The BERT embeddings are generated for the word back. As you can see, the trace shows clear cluster separation, and our method benefits from this because the trace will actively turn the agents away towards the cluster to allow more efficient exploration from an arbitrary start point. For global embeddings, we try to apply our method to the task of word similarity. We generate word similarity lists and present them as word clouds in our paper, and is also shown in the slides. Other than our method, which is coined MCPN similarity in this case on the right, we also apply other similarity metrics named cosine similarity on the left and Euclidean similarity in the middle. So all of these word clouds are generated based on the word win as a noun. So all the words that you see on these word clouds basically are the words that are identified as similar to the word win, and the bigger the text is, the more similar the metrics says they are. And as you can see on the left side, the cosine similarity has many out-of-place tokens ranked very high in the ranking. You can see budget, you can see insight and mandates that are very, one would say not very similar to the word win at all. And but if you look at Euclidean and MCPM similarity lists, I can see that a lot of those words are very agreeable, and they're also very similar. And while Euclidean similarity and MCPM similarity have many in common, we can also spot some disagreements, such as words like low pressure and intertropical in the MCPM similarity list, and storm force and low level in the Euclidean similarity list. All of these results points to a very different but still valid way of exploring the dataset. By applying our method, we also can make distinction between two types of data points. We call them knot words and filament words. For example, the word class on the left is position and the filament, or a thread between major clusters, while the word research on the right is positioned inside one cluster. We can define this distinction by different distribution of the travel direction of the agent. So once the agent is spawned from the blue point, we look at its the distribution of its travel direction. While agents spawned from knot words on the right are spread out more evenly, the agent from filament words on the left travel more in a bimodal or multimodal manner. We have shown some interesting results in our paper, but we're still at the very beginning of our research. So for future work, we'd like to apply our method to well-known similarity list datasets like Simlex 999. And since word embeddings can have very high number of dimensions from 500 to 1,000, we'd also like to reinvent our model so that we can run our simulation in the original high-dimensional space. And we'd also like to investigate further into the knot and filament word distinction. We're very interested to know whether this distinction corresponds to any semantically meaningful separations and how they are distributed in the datasets, and just generally insights that we can make by separate the data points in the knot and filament word distinction. And that's it for our talk, and thank you for listening.
Tech C, can you confirm we're ready to go? And Henry, would you share your, at least unmute yourself? There we go. Okay. Thank you, Henry, and your co-authors for that presentation. I'm not seeing any questions in Discord or in YouTube, but I was actually quite curious about a couple of things in the work that you're describing here. I think back to my days in chemistry many years ago, and there was a process called diffusion limited aggregation, which is, for instance, the process by which snowflakes form and many other things. So I have two questions. One is, where did the original inspiration in the bio-inspired come from? What was the original impetus for this particular model of how to structure the space?
I might take that, actually.
Yeah, please.
Yeah, sure.
So the original design of the model was in cosmology and astrophysics, where we actually detected the cosmic web structures with these based on positions of the galaxies. And the connection to language was just that it's a similar network-like structure, except in a higher dimensional space. So in this work, we applied in the reduced or projected 3D space, just because we don't yet have a model that can run in 500 dimensions and produce viable density estimates and such. But it's a very good observation. It's very, like Laplacian instability-like model. So diffusion limited aggregation is something that probably relates to it. The rules are a bit different, but yeah, it's an interesting connection for sure.
And you get a somewhat different data structure underneath, right?
Yeah.
Hierarchical structure instead. It looks like your visualizations are all, the actual visual representation is 3D.
Mm-hmm.
What about using a 2D reduction? Having it be shown in 2D?
We're showing it in 2D, but I mean, it's the dimensionality reduction itself is getting us a little bit unsure about is it like fully representing the data itself? So like reducing it further to 2D might further like reduce the information that we're trying to capture.
Do you think there are implications for either of the two things that we've just considered, alternate physical systems or 2D versus 3D, for the kinds of relationships that you can see between the language elements?
Yeah, I mean, for one, the 3D space is much richer in terms of the topologies that it permits. In 2D, you basically cannot have like crossing edges without actually mixing the agents, like traveling from one to the other. Whereas in 3D, you can actually create like arbitrary topology without intersections of those filaments or those connections between them. So it's definitely a better space to unfold structure into, but of course we are going from 500 or 300 down to 3, so it's still a significant reduction, and that's something we need to look at.
Absolutely. Well, great. Thank you very much for your presentation. Everybody, please express your appreciation through emojis and so on.
Thanks, everyone.
All right.
Hey everyone, my name is Daniel and I'm a student at the Chair for Data Analysis and Visualization at the University of Constance. Amongst others, I've been working with Matthias, who gave a talk at last year's workshop about visual musicology. Using the methodology transfer as presented in that talk, I introduce you to a novel visualization of rhythm that augments sheet music called the Rhythmic Fingerprints. In this first example, can you recognize any difference in the rhythm between the two measures? It's hard to spot, right? And you won't, because these rhythms are identical. Now take these two measures for a change. Do you think that there's any rhythmic subpattern common to both of them? Again, difficult to answer with a lot of notes, huh? Turns out that there are even multiple common subpatterns, and here are just two examples. Lastly, let's take a look at this larger excerpt. Can you tell whether there are any rhythmic patterns that appear more than once? It would take you some time to go through, so here are just some examples I identified for you. As you've seen, none of these questions have trivial answers, yet all of them are part of what could be the analysis of rhythm in a new piece of music you encounter. As for rhythm, we use two defining dimensions, namely onset and duration. Here onset defines the point in time when a sound sets in, as you can see with 0, where the half note starts to play. Meanwhile, the duration is the time that passes between two onsets. For example, the half note sounds in between the onsets 0 and 1. Focusing on the second dimension, the duration, we can make use of the so-called rhythm tree for further characterization. In this exemplary measure, the rhythm tree illustrates the division of the measure's duration into the different notes. The half note represents the first half of the measure. The remaining half splits equally amongst the quarter and eighth notes, which again bisect their half. Generalizing this idea, the rhythm tree on the right is similar to phrase structure trees used to describe sentences in linguistics. It enables to express a wide spectrum of rhythms. While this instance of the rhythm tree provides powerful capabilities to describe rhythmic patterns, one is to be cautious as it only applies to simple meters. In addition, we distinguish between notes and rests to assign them complementary color scales, which we will later use in the rhythmic fingerprints. With the theoretical background established, it remains to figure out how we can visualize the rhythm tree. As I teased in the introduction, we rely on methodology transfer to take inspiration from an already established solution in another domain. Therefore, our more general problem statement is how to visualize a binary tree. With all that being said, genealogy turns out to be a domain of particular interest. Amongst other things, genealogy researches the ancestry of a person, which happens to lay out as a binary tree. A fan chart is a common method to visualize such an ancestry. The radial display concentrically shows generations of ancestry, with the oldest generation being on the outermost disk. Now we got the analogy between the rhythm tree in musicology and the ancestry in genealogy. As the fan chart visualizes the latter, what can we come up with in musicology to visualize the rhythm tree? A radial display of concentric circles with the longest duration at the center and the shortest one in the outermost. As a foundation for the design of the rhythmic fingerprint, we use a radial display. This decision is reasonable as we operate in the time domain and rhythm is inherently cyclical. Besides, humans are used to the clock metaphor and hence should have an easier time reading this radial visualization over a linear design. Starting at noon, time moves clockwise and each concentric circle represents the duration of a whole note divided into 32 arcs at most. That is, the outermost disk represents 30-second notes, while the innermost disk represents the whole note. To represent rhythm in the skeleton, we use the previously mentioned color scales and fill the arcs corresponding to the notes. In this exemplary measure, the half note appears at the beginning, hence at noon in the disk for half notes. Looking at the rhythm tree, we use the color assigned to half notes and fill the arc like this. The quarter note occurs after half of the measure and therefore at 6 o'clock. The last two eighth notes follow the same principle. The example we just exercised consisted of a single voice. Now let's see how the rhythmic fingerprint works out for two or more voices. To make things a little easier, we first pretend to have the two voices in two separate measures, generating two rhythmic fingerprints. As previously, we color the first rest according to the assigned color scale. The following dotted quarter node is somewhat special. As you may have recognized, none of the disks in the rhythmic fingerprint represents the duration of dotted nodes. Therefore, we display dotted nodes in the disk of the next longer duration. In this example, the dotted quarter node appears in the disk of half nodes with an adapted arc length that represents 3/3 of a half node. This also greatly illustrates that nodes can appear outside of the predefined arcs in the disk. In this joint rhythmic fingerprint, there are two things you should take note of. Firstly, we prefer the presence of sound over its absence, such that a node will be displayed if it appears with a rest of the same onset and duration. Secondly, the multiplicity of nodes, as with the last 8th nodes, in each voice is not specifically treated in the rhythmic fingerprint, as it does not change the perceived rhythm. If we repeat the procedure that we just walked through, we can annotate every measure of a score to arrive at an augmentation of common music notation with the rhythmic fingerprints. To validate the usefulness of the rhythmic fingerprints, we conducted a qualitative user study with 4 novices and 4 experts. During the analysis, the participant received 2 scores in random order, with the rhythmic fingerprints annotated on one of the sheets only. For the user study, we used the 2 scores area and variation 7 from the Goldberg variations by Bach. The former plays in 3/4 time, while the latter uses 6/8 time. Both pieces consist of 64 measures, exhibit similar complexity, and have a form of AB-AB, CD-CD. These similarities are the primary reason for us to use these 2 scores. During the analysis, we asked the participants to annotate all rhythmic patterns that they could find, preferably starting with the longer ones. Here you can see an example from one of the novices. On the left are their annotations for area, without the rhythmic fingerprints, which they exercised at first. On the right, you can see the annotations for the second score, variation 7, with the rhythmic fingerprints augmented. Their improvement with the rhythmic fingerprints agrees with the positive feedback from the remaining participants. Most of them favored the rhythmic fingerprints over the common music notation to spot recurrent rhythmic patterns. Also, the participants reported that the rhythmic fingerprints eased their analysis and created visually clear patterns. This allowed them to find similarity and dissimilarities more easily. Besides this positive feedback, the participants were worried that the used colors are too similar, which made it difficult for some of them to get used to the rhythmic fingerprints. On top of the feedback by the participants, we want to shortly discuss 2 limitations of the rhythmic fingerprints. As we've seen while iterating the design, the rhythmic fingerprint encodes all voices present in a score. On the contrary, though, it's not possible to reconstruct the encoded voices from the rhythmic fingerprint. For example, as seen earlier, the rest of the second voice is not visible in this rhythmic fingerprint. With our instance of the rhythm tree as the foundation, the rhythmic fingerprint does not represent every time signature equally well. 2/2 and 4/4 time do not pose any issues as they fit into and fill up the duration of a whole note. However, for time signatures with a total duration of less than a whole note per measure, the rhythmic fingerprint will exhibit white space. These time signatures also illustrate the ambiguity of rhythm, as the simple meter of 3/4 time and the compound meter of 6/8 time look the same in the rhythmic fingerprint. That's because our instance of the rhythm tree does not take this ambiguity into account and is suited for simple meter only. Lastly, the rhythmic fingerprint cannot represent the red-colored group of time signatures up here, as they exceed the total duration of a whole note per measure. Rendering them regardless would inevitably lead to overlap or 2 rhythmic fingerprint instances. We want to improve the visualization design regarding voice separation and time signatures as we've just elaborated. Besides, we intend to align the rhythmic fingerprints region of interest with the context, as rhythmic fingerprints might not always adhere to the boundaries of measures, but could start somewhere in the middle, as in this example. And lastly, we plan to experiment with the display of dotted nodes. Currently, they are moved in the disk of the next longer duration. However, their display could turn out to be more intuitive if they remain within the disk of their base duration. Thank you very much for your attendance. I'm very happy to discuss the Rhythmic fingerprints and their further development with you.
Okay, well, I hope the video is done. So we'll jump in here. If you have questions for our speaker, please enter it into YouTube or Discord. Meanwhile, I'll ask a broad question that I was thinking about. I played music just as a student many, many years ago, and it looked like this potentially could be good for learning purposes, right? Especially to just get a sense of the rhythm for playing. It also looks like it's good for analysis. But then I wondered, would it also be good for say a professional musician? Would this be the sort of thing that one could actually read while playing? And also, does it somehow capture the subtleties that you have in rhythm for more advanced playing? So think of variation in tempo that goes beyond just the time signature.
So we've been not aiming at any specific use case, so this might be suited for the analysis, like a really professional musician, or for the performance, or even to start getting into music or for education, as you pointed out. Mm-hmm. Well, first of all, the rhythmic fingerprints are always tailored towards the notation, so everything that can be expressed in the notation could potentially also be visualized in the rhythmic fingerprints. However, for the moment, we are just starting to develop this visualization, and we haven't figured out how to display all of the different variations of nuances in rhythm that could occur. So, for example, if you have triplets, which are even quite common in music, that's something which we haven't figured out yet how to display. And if you refer to performers, then it's even more difficult, because very often performers might not adhere to what is actually displayed in the common music notation. So this could be sort of a problem that we might want to tackle in future iterations of the rhythmic fingerprints.
Certainly, certainly. One more maybe relatively quick question here. Thinking about your title of rhythmic fingerprints, right? And I think back to both Martin Wattenberg's arc diagrams, which worked on a detail level, but by and large, as fingerprints, they worked very well. And of course, Daniel Keim and others own literature fingerprinting. This would have been around 2007. But in both cases, in many ways, they worked better as the actual fingerprints for comparing between the objects, right? In this case, the individual measures on your part or entire documents. Where do you think that the balance lies in the technique you have currently between, say, seeing them as overview for comparing versus looking at the details and comparing in that manner?
So if you think about common music notation itself, then musicians often engage in close reading, which has been sort of the state of the art for many years. And there are also a lot of other related work for visualizations that tackle rhythm in a sort of overview, completely ditching the common music notation. However, as we have seen in the development of common music notation, there were a lot of suggestions for other notations which have not been adopted by the community. So our idea was to provide a visualization that could be augmented with the common music notation, since people from the community really like that. And given the history, we did not want to provide an overview visualization that completely neglects the common music notation. So we use the measure as a sort of region of interest to provide a good balance between overview and the detail that musicians are used to.
Okay, a lot of hard data to visual design choices to be made, to be sure. All right, thank you very much. Let's please express our virtual appreciation for the speaker and the other authors.
Thank you.
Hello everyone, this is Alejandro Benito-Santos. I'm a research assistant and PhD candidate at the University of Salamanca in Spain. And I'll be talking about Pilaster, which is a collection of citation metadata extracted from publications on visualization for the digital humanities. So it is very related to the contents of this workshop, as you will see, which we have been following closely since its creation, and it has generally been very inspiring to us. So thanks for that to the organizers. And this all departs from our intention to characterize visualization for the digital humanities, and it all started with a paper that was published in Computer Graphics and Applications this year that was built around the idea of an analysis on keywords. And we decided to take a part of this dataset and make it available and easy to use for interested researchers. So we provide a normalization of author and publication aggregations names, and that enabled us to build more comparative analysis, as you will see. And also we provide the code and in a Colab notebook and spreadsheet that you can use. Since the beginning, we were trying to characterize visualization for the digital humanities. So that took us to the question of what digital humanities are. So as you know, it's not easy to answer these questions, for this we had to go to the literature and browse through the different definitions, and we especially like this one by Rafael Alvarado from 2011 that said, let's be honest, there is no definition of digital humanities if by definition we mean a consistent set of theoretical concerns and research methods that might be aligned with a given discipline, whether one of the established fields or an emerging transdisciplinary one. And he continues saying, how else to characterize the meaning of an expression that has nearly as many definitions as affiliates? So it is a social category, not an ontological one. So this was the key sentence that helped us build the rationale behind the study. So when you want to study a field in science, so you usually use keywords, right? So you go to an online database and input these keywords, and you retrieve relevant papers and analyze them and create the survey. But in this case, we had to depart from the authors themselves, right? The authors who had identified themselves with the idea of visualization and digital humanities. So for this, we went to two main venues. So one main venue was this workshop. So we extracted publications that were published in this workshop in previous years. And also we went to the Digital Humanities Conference and its peer journal, the Digital Humanities Quarterly, from which we extracted publications. So it was quite easy for us to go to and extract metadata from the VIS4DH workshop. So all papers are published in the website. So we just downloaded them and extracted metadata from there. And it was slightly more complicated in case of polling digital humanities publications. We capture the author's intent to employ visualization in their research by matching a regular expression against the title or list of keywords or topics. So, we knew there were some downsides with this approach, but in the end, we decided that employing this regular expression was good enough for us to poll or to create a sensible sample of the field, and it also made the study reproducible. We were okay with this in the end. So, but we know there might be some papers missing in this case. So in the end, the seed dataset contained almost 120 papers, and they were distributed in time, as you see on the chart on the right, and that dot plot. So 2016, that was the year in which this workshop started. Was quite a prolific year. And from these papers we started citations, and that were probably according to the publication year in the chart you see on the left. So there's a slight difference between DH and these authors in the dates of the works that they cite. So this could be due to differences in the deadlines for the Humanities conference and this workshop. So there were also like around 280 resources that were cited from both sides of the collaboration, which is also an interesting subset that might be worth looking at. And on the right you can see a whisker plot showing differences between reference or lengths in reference lists in both sides, on papers on both sides of the collaboration. So this is related probably to the also to the different way humanists have to communicate their research, which is something that's been discussed in the past by other researchers. So this the citations dataset comprises different types of resources, like they are mainly articles and conference papers and books, but there are also some other interesting resources like online data sets or PhD theses that are linked to a large number of different topics and also might be worth having a look. So here are the different fields that compose the data set and the different tables. So we won't be discussing them in detail now as we don't have time, but we invite you to go to the paper and go through them. They are all described there. So in the end, this was all put in a Google spreadsheet, as we said at the beginning of this presentation. That's ready to use for you. Finally, we built some simple use cases that, well, the main aim of them was to illustrate how the dataset could be used, and it was a way to show you how to get started with working with the data. So we conducted a couple of comparative analyses that we like, because they usually set light on possible potential areas of collaboration or potential partners, things like that. So here you can see the cited publication aggregations from the VIS site. So unsurprisingly, the transactions on visualization and computer graphics, it's at the top. Also the Digital Humanities conference is cited quite a lot, and then some other venues related to visualization research, such as Computer Graphics Forum or EuroVis or Keim. And this is the same, but for the Digital Humanities side. So the Digital Humanities conference is cited the most, and then it's followed by transactions on visualization and computer graphics. So this is the same as it happened in the VIS side. So this appreciation seems to be mutual, and then you can see other venues or journals related to humanities research that I invite you to explore. And finally, we have cited publication aggregations. So by it's the same but aggregated that was presented in the two previous slides. And we can see differences in some journals. So, for example, the Digital Humanities Quarterly was cited more by researchers in the Digital Humanities side, as well as some others. So we continue with this example, and so publications that were cited exclusively from one of the two sites. So here we can see, for example, the International Conference on Document Analysis and Recognition, or the annual meeting of the Association for Information Science and Technology, Semantic Web, which we haven't seen many approaches related to the semantic web in this workshop. So, well, we know that's true that there are many more different themes represented in the DH4VIS part of the dataset, but in any case, it is I think it gives you a good idea of what are the themes that have not been covered in this workshop yet, so it might be worth also having a look. And finally, we built a co-authorship graph that was also a simple example, but it already yielded some results, like the number of authors published in both sites sorry, is low, so around 3%. So this is still shows the large gap that is between the two communities. And also that these communities appear to be larger, so the collaboration is articulated in different manners in the VIS side and in the DH side. So we can see also some nodes that connect different parts of the collaboration, like they are there. So we hope that in the future this collaboration or these two sides become closer, so we start seeing more people from the DH side in this workshop and also the other way around. And finally, to use the dataset, you can also go to that URL, and you also need to make sure that you copy the spreadsheet onto your own Google Drive and run the Google Colab notebook. Just give it permissions and you should be ready to go. Okay, so that was it. I hope that you found that interesting, and I'll be now ready to take your question.
Okay, thank you for that talk. Everyone, please be posting your questions in Discord or YouTube. Right? I'm feeling like I'm going to end up asking all the questions myself in the session, and that's just no fun at all. So obviously it's important to do citation analysis like this, and any improvement on the methodology of doing that is much appreciated because it's so difficult. I'm wondering in particular how we should go about dealing with just how kind of diffuse the meaning of the phrase digital humanities is. I'm still not clear that I have an understanding of what constitutes digital humanities. In particular, do you think that there are maybe other broad areas of effort that don't go at all by that name, that it would be worth considering and somehow including in the umbrella of the citation study that you've been doing?
Certainly, thank you. So certainly, I think that there are some disciplines that could fit into this study. Actually, I've been asking myself this question of what digital humanities are for some years, or especially what visualization for the digital humanities means. And I have another study that I mentioned in the presentation that was oriented towards the analysis of the keywords of this paper. So I ran different kinds of concurrence, and the main aim of that was to get a perspective or a general view of the main disciplines that compose visualization for digital humanities. So there I got for example, a lot of text analysis, NLP, text alignment, all these kind of things. But I also found a lot of 3D visualizations, like related especially to archaeology and reconstruction of ancient buildings. These kind of things are also very interesting and much interesting, and are probably not seen, for example, in this venue very often. So yeah, I hope I can continue expanding on this definition and redefining it as I go, because I think that's part of the fun, right? Of being involved into digital humanities research. But I don't think there's a need for a definite answer. And I agree with Alvarado. I mean, I think that trying to obtain like a golden standard definition, it's probably nonsensical in a way. So I think that as we all go and publish papers, for example, in this venue and discuss what digital humanities are, then we keep redefining it, right? So we are part of the digital humanities. We are that definition, the people who make it.
No, absolutely. And I think that kind of inverting how we look at things, by looking at the history of citations and the landscape of papers and citations, maybe we can get a sense of whether we should even be naming it one thing or multiple things or not. Yeah, so just getting a picture of the landscape is helpful. We did have a couple questions come in. Lauren Tilton asks, she's curious if they are considering adding DSH, since it's the journal of EADH ADHO. And I'm sorry, I don't know what those acronyms are. Probably it's a journal title for scholarly organizations.
Yeah, this is something that we considered. The problem is that we couldn't follow exactly the same methodology to include these papers from digital scholarship in the humanities, because we couldn't get the TI files for these papers. I don't think they are published in this format. We couldn't go in the same way as we did with the Digital Humanities Quarterly or the Digital Humanities Conference. So we decided to leave it aside for the time being. But it's true that probably this journal should be included too in future studies.
So a couple of questions. We need to be quick here, but do you see any way of discerning the relationship between the various involved fields and disciplines? And there's kind of a related question about what is the most interesting eye-opening finding of the analysis, in your opinion?
Yeah, well, the only feasible way that through the years I think I found out is the keyword analysis, because basically making comparative analysis between these disciplines it gives you different subsets or sets of keywords that you can analyze and see what is specific to one discipline and what it has in common with other disciplines that compose the digital humanities. So this is why I'm very interested in the analysis of keywords, because in this case they tell you a lot about digital humanities themselves. So.
Okay, thank you very much. Everybody, please express your appreciation, and we'll move on to the fourth talk of the session, which is visualizing a large spatial temporal. We're presenting the video, and we'll be here for the questions.
We will demonstrate a generous interface in the form of an interactive web-based visualization system for the exploration of a large spatiotemporal collection of historic photography. It's the work of an interdisciplinary team from the University of Richmond consisting of Taylor Arnold, Nathaniel Ayers, Justin Madron, Robert Nelson, and Lauren Tilton. In recent years, cultural institutions have made extensive commitments to the digitization and publishing of their collections where possible over the web. As a result of this, scholars working in the public and digital humanities have developed many different applications for the analysis of particular dimensions of a collection, such as tools for exploring spatial components, textual components, temporal visual components. However, somewhat less attention has been paid to approaches for visualizing many unstructured components of a collection simultaneously. So in this talk, we'll present a web-based visualization system around the concept of a generous interface to explore 170,000 historic photographs. And this serves as a case study for how we can actually integrate the visualization of many multimodal components simultaneously. So the collection that our case study is built around is called the FSA OWI, the Farm Security Administration Office of War Information Photographic Archive. It documents American life during the Great Depression and World War II. The photographs are physically housed in the Library of Congress and include iconic photographs such as Dorothea Lange's Migrant Mother, Gordon Parks's American Gothic, and Arthur Rothstein's photos of the American Dust Bowl. There are over 170,000 photographs currently in the collection, mostly black and white images, but there are several hundred color images. Because they're a work of the federal government, all of the images are in the public domain, and all of the images have been digitized. In fact, they've been digitized twice, once as one of the first large digitization efforts in the 1990s, and then again in the last 10 years. So myself, Lauren Tilton, and in collaboration with Laura Wexler, constructed an interactive website, which we called Photogrammer, between 2012 and 2016. The idea was to offer a new approach to accessing and visualizing the FSA OWI photographic collection, providing different ways of viewing the collections spatially, temporally, and through advanced search features. However, as noted, due to the technical limitations at the time, each of these are provided as separate web pages that are all linked to one another. So I'll show you an example of what it looked like. So this is what Photogrammer looked like from roughly 2017 to 2020. So the landing page is an interactive chloroplast showing where photographs were taken in the United States. And this search could be respecified by selecting a particular range of years or a particular set of photographs in the upper left-hand corner. It's possible to zoom in and out on the map, click on a particular county, and then if we click on the see 145 photographs, for example, after clicking on Jasper, Iowa, we open up a new advanced search page which show all of the photographs in that particular area and particular time period that were selected in the search. So here are small thumbnails of the 145 photos from this particular county. And then clicking on one of those images opens up a page specifically about the image and contains metadata such as its caption, photographer, when it was created, its call number, and also based on textual similarity, photographs that contain similar captions. So what we wanted to do was apply the concept of a generous interface to this collection in order to take what we really liked about the original version of Photogrammer, update it with some modern technological stacks, and make it so that each of these components, which worked well on their own, were more tightly linked and coupled together so that people could seamlessly look at the different components of the collection all at once. And so we wanted to use this idea of a generous interface, which is a conceptual shift from the singular narrow interaction of a keyword search to interfaces that communicate the scale, scope, and richness of a collection. And we like to think that this was actually in the back of our mind. We didn't have the term back in 2012, but that is what we were trying to do with Photogrammer. But I think a full realization of it just was not possible 9 years ago when we started thinking about what technologies existed and how could we use them. So in our redesign of Photogrammer, we wanted to take these ideas of a generous interface and integrate them for a more integrated user experience. So search results would interactively link between the maps, the timeline, the themes, and allow users to look at all of them simultaneously without leaving a single page. So this is what the new landing page for Photogrammer looks like. So you'll see there's still a chloroplast map now on the upper right-hand corner showing where the photographs were taken. But at the same time, we also have a timeline showing when the photographs were taken and by whom in the lower right-hand corner, and also a selection of photographs and their thumbnails and titles and some metadata over on the left-hand side. So already this captures, you can see, elements that were great about the original version of Photogrammer, but but adds more of a generous design to it because each of these elements are instantly available to a user, and as you click on one, they instantly change on the other panel. And one thing we really wanted to change about the site is that this is fundamentally a collection about photographs, and so we wanted to center the photographs the second that somebody landed on the site. So if we click on any element of this plot, it will update the other frames. So if I click on Texas in the map, it'll zoom into Texas. If I click on the photographer Russell Lee in the bottom right-hand corner, it will select just the photographs of Russell Lee. That will in turn update the choropleth map, and also all of these update the photographs on the side. So now we were seeing just the 4,031 photographs that Russell Lee took in the state of Texas. There are other visualizations. We can't fit all of them on one screen at the same time, just due to the size of screens. But these don't open a new page. You click on the other visualizations up in the upper right-hand corner. So, for example, we can click on themes, and that becomes an overlay on top of the map. And so this shows an historic thematic organization of the collection. And as with everything else, as we click on these subcategories, it updates the photos on the left and the timeline on the bottom. Another thing we wanted to make sure that we had in the new version of the site, and we wanted to continue to have and improve, was the idea of a recommendation system. So once a user really gets to a photograph they're interested in, helping guide them to other photographs in the collection they might be interested in as well. So the original recommendation system was built on textual search, which was okay, but didn't add a whole lot more to an advanced search page because you could already search by a keyword. So our new version is based upon visual similarity, so using ideas from computer vision. So here, for example, we've selected a photograph of a woman in uniform in front of a storefront with the textual signs inside of the storefront. And the similar photographs have found photos that look similar. So in this case, the photographs are all of other storefronts, signs in front of them, and actually two of them even have someone else in uniform. So it does a very good job of finding things that are very similar to this image that you otherwise could not find with any sort of search. And they may not be related spatially, temporally, by any other metadata category. So these are really finding these interesting ways of going across the collection that you may not find with any of the other search features that we have available. So in conclusion, the redesigned version of Photogrammer offers a web-based visualization and search interface with numerous improvements over our already successful original version of the site. It offers a more integrated user experience with a number of tightly connected elements that are all interactively updated with one another. So future work on the project will focus on turning the codebase, which is already freely accessible and open source, but turning into a more documented framework that can be used with other collections that have some or similar, or maybe some subset of the features that are present in Photogrammer, so that we can do these kinds of interactive visualizations with other collections. So, thank you.
Okay, it looks like we're back live again. We had one question come in on Discord. One of the things I found interesting about the old site was how it revealed the photographer's historic itineracies across the US. Is that still a possibility? How might you integrate that into a generous interface?
Oh, yeah, that's a good question. So in the video, I was highlighting the choropleth map, which shows the counties. And on the county map, it's harder to see the trajectories of the photographers. But on the top, you can actually change the map so that it looks at the city level. And there you really see these treks across the country where people would get in their car and drive, and you can actually see them, follow them across the country. An issue with the Photogrammer data or the FSA OWI data is that we don't have city data for everybody. We sometimes only have county data. So we start with the county data. So you have all the photographs, but then you can switch on the city view and see the original one. So we've just sort of switched which one is the default map to try to highlight all the photos. But yeah, that is still there.
Okay. Just another quick question, also coming in on Discord. Are generous interfaces synonymous with dashboards? Could generous interface approaches be the solution needed for dashboards?
I think there's some similarities, but also differences with dashboards, because particularly with generous interface concept applied to something like Photogrammer, the idea is that we're going back and forth between a large scale collective view of the collection, like where were the photographers taken and by whom and in what categories. But then the idea is that you actually want to get into the data itself, like eventually, and everyone that we've done user testing with very quickly gets into and actually looks at an individual photograph and reads an individual caption, and then comes back out, or maybe uses the recommender system to get to another record in it. So for me, the dashboard concept, the thing it's kind of lacking is that it's only looking often at the aggregate level of the data and the high level patterns, but it doesn't actually connect you to the original data. So it's sort of like generous interface to me is trying to combine the search interface, which gets you into the actual collection, with a high level holistic view of the collection. And so maybe a good way to think about it is it's putting those two together, so that you can actually see the real records, be them visual, spatial, textual, and then also see them at scale and put the two together.
Okay, nice.
Yeah.
Thank you very much. All right, everybody, please thank Taylor with your claps and so on. We will now progress to the various lab talks.
All right. Thank you, Chris. So my name is Menna El-Assady. I'm moderating our last session for VIS4DH this year, and it's the second lab talk session. We will have 6 back-to-back talks. As you've heard, the lab talks are a new format that we're introducing this year so that different labs can connect and collaborate on different research projects. And we will not have any questions after the lab talks, but we encourage everyone to go to GatherTown or to Discord and get in touch with the presenters. And with that, without further ado, I'll present the first lab talk, the Sussex Humanities Lab, and the presentation is given by Tim Hitchcock. So Tim.
Great. I hope you can see my screen and can hear me.
Yeah.
Is that a yes?
We can hear you. We can see your presenter screen.
Fantastic.
We can see you yourself.
Okay, great. I'm here to present a piece of work that Ben Jackson and I have been developing for the last 4 or 5 years, which is about as long as the Sussex Humanities Lab has existed. It's really an exploration of how we might visualize and interact with large-scale structured data in the humanities, and represents, if you like, the kind of work that the Sussex Humanities Lab is doing that should be of greatest interest to this this particular audience. Now let's see if I can get this. Yeah. And it's based around something called the SHL macroscope, and that emerged from the founding commitment of the Sussex Humanities Lab, and this is everybody having a good time, to pre-COVID, of course, to encompass the work of humanists with data scientists, social scientists, and media theorists to, as our founding document promised, make good things happen. And initially, we built on the work of Bill Turkel and I did to visualize a couple of 100,000 trials held at the Old Bailey in London between 1674 and 1913, which we digitized as the Old Bailey Online. There were around 125 million words, and no one really knew what was there. But what Ben Jackson and I then went on to explore, sorry about that. Let's see if we can get that next slide. Yep. Explore is how we might apply those same methodologies, if you like, that process of visualizing data at scale without actually going down the route of network analysis or clustering, to look at other kinds of structured data sets, including things like the library catalog at the University of Sussex, the catalog of the National Archives at Kew in the UK. We were also using the same methodologies to explore and visualize and work with 700,000 odd items from the bibliography of British and Irish history, which is one of the screenshots there, and also the oral history of the BBC, which is a project that the lab has been spearheading. And in parallel with that, we've also been working in VR and text-to-speech audio. And the thing about the old Dick Bailey material is that, as well as being a lot of trials, each one is a drama in its own right. They also form the largest collection of recorded speech ever published, with the possible exception of some of the parliamentary series. And because we know where the speech took place, we can both recreate the courtroom and start to think harder about the programmatics of conversation, the back and forth of dialogue. And our VR courtroom was recently used as a basis for the sets of the television series Poldark, if you like that sort of thing. But more importantly, we are again moving outwards to intuitively find patterns at scale. Now, this is 30-odd trials. It's what 30-odd trials look like when you divide up all the speakers, where the speech of defendants, judges, lawyers, and juries are seen as a system of exchange. And this is what 30,000 trials look like when you project them onto the walls of the lab at Sussex. And really, all we're really trying to do here, and what I think exemplifies what the lab at Sussex is trying to do, is not to do close reading or distant reading or math-led analysis of text. We just want to explore data at scale and look at all the patterns that appear to us in that data as humanists. Thanks much.
Hi, I hope that is all working. Hello everyone, I'm Olivia Vane and I'm going to be talking about the British Library Digital Scholarship Department, where I work as a research software engineer. So the British Library is the national library of the UK. By law, we receive a copy of every publication produced in the UK and Ireland. We've got up to 200 million items, including 14 million books, 310,000 manuscript volumes, 4 million maps, websites, television, and radio news. And about 5% of this is digitized or born digital. The Digital Scholarship Department at the British Library was founded in 2010 to support the innovative use of the British Library's digital collections and data. There are about 18 of us in the department currently, and data visualization has really been a part of this right from the beginning. So I'm going to talk about how the department works to promote, support, and innovate in data visualization for digital humanities in 3 areas: staff training, the British Library Labs team, and also in research. So firstly, training. Since 2012, the department runs the internal digital scholarship training program, introducing, encouraging use of, and upskilling staff in digital and computational methods. And the Data Visualization for Cultural Heritage Collections course introduces key concepts and teaches how to make simple visualizations with collection data. For those interested in more advanced topics, like an introduction to D3, we also run informal hack and yaks. You can see the logo here, stepping through technical tutorials. Secondly, the British Library Labs team promotes, inspires, and supports the use of the library's digital collections and data. They work on projects with external researchers, software developers, educators, entrepreneurs, community activists, and artists from around the world. They've helped scholars map data for research, create apps connecting the public with poetry in the collection, and created unusual and experimental visualizations of cataloging data. The final element here is research, namely the Living with Machines project, which is actually a project that I work on. This is a large multidisciplinary research project based between the British Library, the Alan Turing Institute, and other academic partners. We apply data science methods to large-scale digitized archives to examine experiences of the Industrial Revolution in 19th century Britain. Visualization plays a range of roles in this work, supporting analysis, better navigation of the library's substantial collections. For example, this is showing newspaper holdings, and also offering different perspectives on the data, like this animation showing map collection survey history. So to sum up, the Digital Scholarship Department supports and encourages visualization of collections data inside and outside the library, from easy, simple maps and timelines through to more sophisticated custom tools. Thank you.
Hello, everyone. My name is Hannah Jacobs. My pronouns are she and her, and I am the Digital Humanities Specialist for the Wired Lab. The Wired Lab for Digital Art History and Visual Culture at Duke University is a community of students, staff, and faculty using visualization technologies to explore art history, architectural history, and visual and material culture. Our research is largely centered in digital art history, but it also draws on information science, new media, and computational media studies. The community is at the core of our work. Our undergraduate and graduate students come to us with many different intellectual paths in mind. Our project teams, typically led by one or more faculty, include students majoring in everything from engineering to art history, and we also support a master's degree in digital art history and computational media. Since 2009, we've met every Friday afternoon during the semester in our lab space to work on projects spanning continents, time periods, and digital methods. The lab also serves as a classroom for 2 to 3 lab courses each semester, which offer students the opportunity to apply digital methods to their own historical and cultural research. And we take the lab to our data sources, working side by side in archives and traveling together to explore objects, places, and spaces. Together, we build repositories for research and teaching, such as Visualizing Objects, Places, and Spaces, a digital project handbook, Digital Athens, and the Dictionary of Art Historians, as well as the Medieval Kingdom of Sicily image database and Digital Durham. We use visualization technologies such as GIS, 3D scanning and modeling, data visualization, and extended reality to analyze historical themes using data gathered from historical materials and spaces. Examples of this work include the Art Historian Exiles Project and the Book of Fortresses, as well as mapping German construction and operating archives. And we create scholarly visual interactive narratives for online and site-specific exhibitions, such as the Senses of Venice and Cultures of the Sea, Art of the Ancient Americas. While the pandemic is keeping us physically apart, our research teams are busy strengthening our infrastructures and data standards and continuing to produce research with our already digitized materials. We're also exploring different ways to share our projects, such as the Culture of the Sea's immersive web version, which is shown at the right of this slide. And through a university-level Mellon grant, we are expanding our engagement with these technologies in our Department of Art History and Visual Studies through a student-driven project to create modules focused on visualizing cities that will span our curriculum. Thank you very much for your time.
I think there might have been okay. Sorry, hold on 1 second. Okay, sorry about that. At the University of Richmond, we are our lab focuses on using and developing computational techniques to analyze visual culture, as well as how we can use visual culture to analyze computational techniques. So the lab is directed by myself, who's in the Department of Rhetoric and Communications, as well as my colleague, Taylor Arnold, who is in the Department of Math and Computer Science, which we think is foundational to our interdisciplinary approach to these questions and to these areas of analysis. Our lab produces work in several different forms, including more traditional scholarly papers and books that are forthcoming, as well as also developing software, tutorials, and large digital humanities projects. So as a part of this work, we kind of currently are focusing in 3 primary areas. One is how we can use computational techniques, namely computer vision, to think about opening up as a source of possibilities for the digital public humanities, which my colleague Taylor Arnold spoke about just about a few minutes ago in this session with the example of our project Photogrammer. Another that we're interested in is how we can think about distant viewing as a method in theory for information and data science, and how it can be a methodology that allows us to think about how we annotate, tag, and describe images at scale, including photography, art, film, TV, and other sources of visual culture. The third area that we're primarily focusing on is visual culture studies, so kind of more traditional questions in the area of visual culture and media studies, such as formal analysis, visual style, and how we can think about using computer vision to do large-scale analysis with the analytical frames of the fields, such as concerns such as shot detection, scene framing, and others. A major interest to this group might be the Distant Viewing Toolkit, which is an open access open source toolkit in Python that allows you to do large scale computer vision work with different annotators and aggregators that realizes a distant viewing theory and method at scale. This has been with generous funding. We're appreciative for generous funding from the National Endowment for the Humanities for this toolkit as well. Finally, I'll turn to the last piece, which is while we're interested in how can we use computational methods to study visual culture at scale, we're also about how we can ask visual culture and questions about algorithms and computational techniques. So we've also been developing the distant viewing visualization to get under the hood and to actually demonstrate what algorithms are seeing so that we can actually be a part of the critical data studies and critical algorithm studies and understand what these algorithms are doing, ask questions about whether we're comfortable with those decisions and how we might remake AI in the ways that we care about and is informed by our work as digital scholars. As humanists. So that is our work at the Distant Viewing Lab. We love to collaborate. So if you're interested in working together, working across these questions, we'd love to talk and think about what the possibilities are as we work together to remake data viz, AI, with all the commitments of the humanities. Thank you.
We're talking about the metadata schema that we're using to expand upon the mods schema that we adopted for the electronic literature repository. Once again, this repository holds 2,106 works and 25 collections. So there's a lot of data for this multimedia, interactive, experiential work. I'm going to switch now to another screen, and Holly Slocum, who's working with me, is going to talk about the schema. Holly, are you there? Can you unmute?
Yes, I'm here. Yes, this is our ELMS metadata schema, and more specifically our crosswalk document that crosswalks our metadata schema with CEL, which is the Consortium of Electronic Literature taxonomy created by the Electronic Literature Organization, and MODS, which is the Library of Congress's metadata schema. We have crosswalked this to make it technologically readable across databases, but in doing this, we found that we had to flatten the human experience in order to make it computer readable. And what ELMS is seeking to do is expand that once again through defining accessibility features. What exactly a reader needs to do with their body, what the physical body needs to do to interact with the work. Whether it has a critical sonic component, whether it needs perhaps one or two hands to hold a book in front of a computer screen, or what physical elements is required of the reader in order to interact with these kinds of works.
So if indeed the purpose of metadata schemas is to provide a common understanding of what data are composed of, and that's the elements or attributes for the purpose of describing data, then EL's expanded MODS, which we are calling ELMS, addresses the need for an approach that describes this kind of technological and physical accessibility that works require. Once again, we're focused on human-centered works, human-centered activities that include preservation and archiving, curation, documentation, and production. So that is our discussion today, and we're hoping to have some questions about this project that we're doing with the repository. Thank you.
Hi, my name is Micah Vandegrift, and I'm the Open Knowledge Librarian in the Copyright and Digital Scholarship Center at NC State University Libraries.
And I'm Mike Nutt, the Associate Head of Data and Visualization Services.
We're pleased to offer this brief overview of the Data Experience Lab, which is a collaboration between our two units in the library. The Data Experience Lab is a space for data science, visualization, and digital research and scholarship. We provide drop-in support, computing resources, including high-performance computers and specialized software, and various collaboration spaces, and have just launched as part of a building renovation this fall. The DXL aims to be a hub for campus communities working on all kinds of data and employing new research methods and practices, including visualizations, geospatial analysis, open science, and digital humanities. This lab is the product of a 7-year arc from the pioneering visualization work in our James B. Hunt Jr. Library to the current data science and digital scholarship training, workshops, consulting, and project development that we offer.
Digital scholarship on college campuses has often taken the form of a center or lab housed within a library. Libraries have a rich history of how to facilitate digital humanities research and projects. Our own campus digital humanities community was eager to have a shared space in the library to grow their connections with others across the campus. Digital humanities methodologies now include data science techniques like computational text analysis and data visualization. So the DXL was designed to be a shared public space where researchers and students from any discipline could take workshops.
Hi, my name is Micah Vandegrift, and I'm the Open Knowledge Librarian in the Copyright and Digital Scholarship Center at NC State University Libraries.
And I'm Mike Nutt, the Associate Head of Data and Visualization Services.
We're pleased to offer this brief overview of the Data Experience Lab, which is a collaboration between our two units in the library. The Data Experience Lab is a space for data science, visualization, and digital research and scholarship. We provide drop-in support, computing resources, including high-performance computers and specialized software, and various collaboration spaces, and have just launched as part of a building renovation this fall. The DXL aims to be a hub for campus communities working on all kinds of data and employing new research methods and practices, including visualizations, geospatial analysis, open science, and digital humanities. This lab is the product of a 7-year arc from the pioneering visualization work in our James B. Hunt Jr. Library to the current data science and digital scholarship training, workshops, consulting, and project development that we offer.
Digital scholarship on college campuses has often taken the form of a center or lab housed within a library. Libraries have a rich history of how to facilitate digital humanities research and projects. Our own campus digital humanities community was eager to have a shared space in the library to grow their connections with others across the campus. Digital humanities methodologies now include data science techniques like computational text analysis and data visualization. So the DXL was designed to be a shared public space where researchers and students from any discipline could take workshops, perform group work, have project storage, come to open lab sessions, and receive free consultations. One of our provost's top currently unfunded priorities is to launch a School of Data Science at NC State in fall of 2021. By virtue of the data science field, this school will be interdisciplinary as well. The library has a seat at the school's planning team, and we are discussing how to operate existing data-intensive research consulting from that library space. This means that practitioners of bioinformatics, statistics, digital humanities, and more will have a transdisciplinary third space in the Data Experience Lab.
The phrase data experience signals an inclusive approach to the diverse ways that we can experience, analyze, and share data, which include visualization, sonification, and physicalization. This focus on accessibility will help us build a space that will foster excitement, empathy, kindness, and belonging. Since this space is brand new and we opened during a global pandemic, we are still unsure what shape this community experience will have. As the Data Experience Lab brings together our data and visualization department with our digital scholarship unit, we imagine that the service portfolio will offer an end-to-end data research lifecycle, from finding, analyzing, and representing data, all the way to publishing data projects prepared for peer review and disciplinary validation. We are excited to enter this space now and are particularly inspired by the recent white paper from the Turing Institute, outlining a generous future where humanities and data science researchers work together in synergy to realize the full potential of interdisciplinary work. We especially affirm their recommendations for common methodological frameworks, cross-disciplinary evaluations of computational tools, incentives for open and reproducible research, and the development of robust talent pipelines, as well as short skills enhancement courses and workshops and university courses. So in a nutshell, in a brief overview, that's what the Data Experience Lab is, and we hope will grow to be more here at NC State. Thanks for listening, and thanks, Mike.
Thank you, Micah.
Right. Thank you all. All right. Thank you again for bearing with us through this whole day and engaging with all of these wonderful talks and lab talks and provocations in what is clearly a new and experimental format. This is really exciting for us as we start to look for ways to extend these conversations outside of just this one day a year. We were scheduled to present a tutorial at the ADHO Digital Humanities Conference this past summer, which unfortunately had to be pulled, but we hope to connect the VIS4DH workshop to that venue in the future. And if you have any thoughts about what sorts of forums might be useful to this community, other groups or venues that we should reach out to, or are interested in getting involved in organizing, please reach out to us at vis4dh@gmail.com. I want to extend special thanks to all of our speakers, including our invited keynote speakers, paper and provocation authors, and lab talk presenters. Thank you too to everyone involved in organizing this year, including the program committee, organizing committee, and most especially our workshop chairs, Catherine DeRose, Uwe Heinrichs, and Menna El-Assady. A huge thanks goes to the IEEE Viz technical team, who've done a fantastic job helping us all navigate this plethora of digital tools to pull this off. And finally, thank you all for attending. Unfortunately, we aren't going to be able to do what we usually would by trekking together to a restaurant or bar to continue these wonderful conversations over food and drinks. But many of us plan to hang out in Gather Town for a little while after this, and I really encourage you to join us there. Otherwise, we look forward to seeing you at future workshops.
DVR has always been from considerable interest to the scientific community. To this day, traditional desktop setups are the gold standard. However, what if we could utilize DVR in virtual reality? Now you think, VR and DVR are so computationally expensive, how is this even feasible? Come to my talk and we present you a straightforward solution to visualize volumetric datasets with high refresh rates on VR devices.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
Hello. Student competition is intrinsic to the pedagogy of cybersecurity education. At RIT, we have observed that the collegiate penetration testing competition and other related competitions are missing a key element: visualization. In this position paper, we provide an architecture and plan to create compelling experiences for participants and spectators. In doing so, we can potentially attract new talent into the field.
Syringe graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign allurance through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the syringe graph layout optimization. The result shows that our algorithms perform better than the others.
A dynamic graph models changing relationships between entities over time. In this work, we present multi-scale snapshots, a visual analytics approach to provide an overview of a dynamic graph at multiple temporal scales. The approach consists of 3 steps: creating multi-scale temporal summaries, applying graph embeddings, and the semi-automatic visual analysis. The combination of these steps lets us visually explore how temporal and structural properties affect the overall dynamic graph.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, You can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
The daily work of criminalists consists of analyzing relationships in complex data while proposing and verifying multiple hypotheses, often under heavy pressure. This poses high demands on their memory and cognitive capacity. We present Visuland, a tool that helps investigators track their visual exploration and reasoning. It organizes analytical state in a graph structure which can be revisited and shared with colleagues.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIF matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user selected path to justify and reason the AD analysis.
Hurricanes, air pollution, forest fires, urban sprawl, ocean plastics, politics, traffic jams, and pandemics. So many of our modern challenges are geospatial, and so much of our big data is geospatial. How is the VIS community addressing needs to visualize and analyze this data? Our review examines IEEE VIS's recent contributions to geovisualization and geospatial analysis.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
In this paper, we investigate design choices for work-correlate maps by domain experts. We tackle 2 research questions: how do domain tasks influence the design choices, and what equal error projection is preferred. Through a survey, we collected 40 correlate maps designed by 20 social scientists, and our analysis suggests that the choices vary across tasks, the projection was most important, and the equal error projection was preferred.
In a visualization, laying out labels to data points needs to be done automatically with a fast labeling algorithm. We introduce occupancy bitmap. It's a data structure that helps the labeling algorithm to, first, quickly record the positions of existing marks and labels, and second, quickly detect overlapping of labels to the recorded positions.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduced a scalable and flexible way to interactively build hierarchical topics.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variant.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology.